Moving straight on. So I've written out again here my books fell down. The component of the magnetic moment that's parallel to this unit vector J, his unit vector J, dot product. Right? And here's your magnetic moment, the angular orbital angular momentum part and the spin part. You've seen this sort of thing before. Okay. Now take this. This will be then the component of the magnetic moment, total magnetic moment. The spin part and the orbital part along parallel to this. This is the unit vector. So you've got a dot product here. Now to get the potential energy term that you'll add to the Hamiltonian, you take the mu, the magnetic moment, and your dot product with the magnetic field B. In this case, we'll assume it's we'll take the jth component. We'll assume the B is oriented along the z-axis, and hence this will be the z-axis, and it's a small b. Remember the whole point of we're talking the third case of let's see, what was it called? There's the three cases. I need to look in the text just a minute. Oh, the Zeeman, of the Zeeman effect, where you get the splitting of the eigen energies due to the presence of a magnetic field. And in this third case, we're assuming the magnetic field strength is very weak. Okay, so now just multiply this by your B, and you've seen this sort of thing before. So if your J is just think of it as a vector, as L plus S. So you're multiplying this by L plus S. You do this as a bit of homework if you want. We've seen this kind of thing before, right? Now, then put them as operators. You put hats over them, and then you can find what's the correction, the energy correction. And you can rewrite this. That's your energy correction. Rewrite it in this form. So we've got a new G here, a new definition. Now, as operators, you get J squared as an operator. Its corresponding eigenvalue is J into J plus 1. Similarly for the L's and the S's. So you get this expression for your G. Now, why write it in this form? Well, it's just similar to the others. Just writing it in the same way to sort of make it familiar. But the G is now redefined. So this G here is now this, okay? And this particular G is known as the Lambda G factor. I think he's probably not alive now, but I used to correspond with him when I was a student, just before I moved to London to work with David Bohm. And Lunde had a great respect for Bohm. Bohm was one of the pioneers in alternative interpretations of the quantum mechanics, not just, he fought against the dominance of Niels Bohr's Copenhagen interpretation. So he thought a deterministic, Bohm that is, thought a deterministic reinterpretation was possible, invented a whole lot of new things corresponding to that, in line with other big names also not liking the Copenhagen interpretation. We talked about this early in the course. Names like, well, the biggest one, of course, Einstein and Schrödinger and de Broglie, big names. Okay, so Monday. Alright, now you can make a few remarks, like if S is 0, so this drops out, then your J effectively just becomes L, so these two drop out, so this whole term here goes to 0, so G is just 1. Okay. Now if L is 0, these are these extreme cases, so if there's no spin magnetic moment, G just becomes 1, and if L is 0, so in other words no angular orbital magnetic moment, then well, let's see what happens. So if L is 0, J is effectively S, so you get like 2 S's, and J is S again, so 2 over 2 is 1, so G will become 2, which is the same as GS was 2, and here GL was 1. Right? So these two limiting cases where no spin and here no orbital, then you get the results that you'd expect. Right? So let's see, so magnetic moment parallel with this. So your magnetic moment then, as thinking of it as a vector, is parallel to the angular momentum with this kind of thing. Well, that's the general comment. This is very hand wavy. Remember at the beginning talking about this third case where the magnetic field is weak, that text says that the mathematics is too difficult for undergrad level. So this has been a bit of a hand wavy discussion on this third case. So you're not expected to know all the details. Okay. All right. Well, that's the end of the theory portion of this this lecture, and it's a pretty short one. So I thought I'd pad it out a little with some more books and more courses at undergrad level that are coming. Just a minute. One of the 3 books I was going to show you, or I will show you, fell on the floor, so I'm just picking it up now. Now all undergrad courses, right? All part of preparatory undergrad courses needed so that you have enough material to teach yourself, which is the whole point of the whole deGarisMPC series of courses, or lecture sets as they call them, is so that anyone with sufficient intelligence, of course, can teach themselves graduate level, master's PhD level, in pure mathematics and mathematical physics, with some computing courses thrown in. Like the next one I teach, my third course, starting in a week or 2, I guess, will be on theory of computation. So computability, what can you compute, what's impossible to compute, Turing machines, complexity, that kind of thing. Right? Well, I'll introduce to you now 3 undergrad courses, preparatory courses for grad work. And the first one is on particle physics. The second one is a very popular account by a great name, Dick Feynman, one of the top theoretical physicists of the 20th century. And he wrote a popular book called just QED, which of course is short for quantum electrodynamics. And so he introduces in a quasi non-mathematical way the basic ideas, and that's why it's so interesting. And it's by Feynman, of course. Anything he does is always good. And the third one is on knots, K-N-O-T-S. And you may ask, what on earth are knots doing in deGarisMPC? Well, I will take them right through. Actually, they're very important. Knots are a branch of topology, and they have very interesting topologically invariant properties. That means, well, it's a technical definition, but it just means that something topological remains conserved, no matter how you wiggle or change how you wiggle the knot. And that has relevance to topological quantum computing, which is something I'm very interested in. Right, so that's a bit of an overview. Now I'll actually show you the books and say a bit more about the topic. So here's Here's the first one. Okay. Called Introduction to High Energy Physics, which is just another label for particle physics. It's the 4th edition. And when a textbook, especially if it's published by a reputable publisher, this Cambridge University Press, CUP, and you can't get higher than that. And it's the 4th edition,